Welcome back to DC Circuit Analysis. I'm Linwood Fields, your green instructor. Today's lecture is on charge and current. I pretty much follow the Principles of Electric Circuits Conventional Current version, 9th edition by Floyd. So basically, I pretty much follow that textbook from the beginning of these lectures until the end of them. Okay, today we're going to look at current. Now, current, resistance, and voltage are the three main components in circuits. In this lecture, we'll simply introduce current. We are not going to be solving for current in any circuits yet. We're going to do that later. So this is a reminder of the reference textbook. So I put on the first slides or the introduction, the very first slide, so I don't forget. The objectives: know what current is and know the units for current. Understand which electrons in an atom are responsible for current flow. Understand what valence electrons are and their relationship to current. Know how to write the two conversion factors relating the number of electrons to the amount of charge carried by these electrons. And recognize the difference between direct current DC and alternating current AC. Know the symbol for a current source. Electrical charge. The type of electrical charge relevant for us is the valence electrons in atoms. Recall from your science study that an atom is made up of a nucleus and orbiting electrons. And remember, electrons have negative charges. Well, one electron has a negative charge. The nucleus is made up of neutrons that don't have any charge and protons that have a positive charge. Electrons orbit the nucleus at different distances from the nucleus. So the electrons orbiting the nucleus, the farthest away, those electrons are called valence electrons. These are the ones of most interest to us because they are relatively free and we can make them flow. That contributes to current. Here we show a neutral silicon atom. A silicon atom has 14 electrons. And in the outer shell, there are 4 electrons. So this outer shell is the valence shell. So we see that we have 1, 2, 3, 4. So this shell right here closest to the nucleus, and this shell number 2, the next closest to the nucleus. These electrons and those shells don't contribute to the current flow, only the outer electrons. Again, the outer shell is called the valence shell. Electrons in this shell interact with other atoms, for example, in chemical reactions. And in metals, these valence electrons determine the physical properties. For example, the physical properties of electrical and thermal conductivity. Charge. Now, charge has units of coulombs. 1 coulomb of charge is the amount of charge associated with 6.25 times 10 to the 18 electrons. Yes, 1 coulomb of charge is comprised of many, many, many electrons. 1 electron has 1.6 times 10 to the minus 19 coulombs of charge. So 1 electron has a very small charge. Okay, we can form a conversion factor from this relationship. 1.6 times 10 to the minus 19 coulombs per electron, or equivalently 6.25 times 10 to the power 18 electrons per coulomb. Let's work a couple of examples. How many coulombs of charge does 37.1 times 10 to the 16 electrons represent? Now this 37.1 may give you the impression that we have a fraction of an electron, but when we multiply 37.1 times 10 to the power 16, we move the decimal point 16 places to the right and we end up with a whole number. Okay, so first, let's write down our conversion factor. Okay, we have 6.25 times 10 to the power 18 electrons per coulomb. Okay, so now we're going to use dimensional analysis to solve this problem. So we're going to write down what we're given first. We're given 37.1 times 10 to the power 16 electrons. Now in the conversion factor right here, if we use this form, we cannot use same object division. Nothing cancels out. So we have to use the equivalent form, which is, okay, so let's go ahead and write our solution like this. Okay, the equivalent form is there is 1 coulomb per 6.25 times 10 to the power 18 electrons. We see that electrons cancel out. The units we're left with is coulombs. Now we just take care of the number part of the problem. 37.1 times 10 to the power 16 divided by 6.25 times 10 to the power 18 gives us 0.054 coulombs. So 0.054 coulombs is the amount of charge associated with 37.1 times 10 to the power 16 electrons. So let me erase this. Okay, how many electrons are in 3 coulombs of charge? So again, we're going to write down what we're given. We're given 3 coulombs of charge. We're going to use dimensional analysis. This is our one-line solution. Dimensional analysis is such a beautiful tool. Okay, so we're going to use our same conversion factor, but this time we need this 6.25 times 10 to the power 18 electrons in the numerator. So 6.25 times 10 to the power 18 electrons per coulomb. We see that coulombs cancels out. The units we're left with is electrons. Next, we multiply 3 times 6.25 times 10 to the power 18, and we get 3.7 let me erase the units, 3.75 times 10 to the power 19 electrons. Okay, let me go ahead and erase all of this. So the number of electrons and 3 coulombs of charge is 3.75 times 10 to the power 19. Quite a few. Valence electron motion. Now let's look at how those valence electrons in the valence shell move around. They move in random directions because of their thermal energy. But it's key to realize that they have no net displacement. And I'm going to, there's no net displacement. I'm going to show that in this, in a little animation that I made. So we have 2 electrons. Of course, electrons don't have color. This one I just labeled blue, and this one I made it orange so that we can kind of follow the motion. But just kind of realize that these electrons are going to be moving around because of their thermal energy, but overall they're not going anywhere, which means they have no net displacement. Okay, let's see what it looks like. They're moving around, but they end up in the exact same spot. It's a little bit of an exaggeration, but that's pretty much what happens. They don't have a net displacement. Now, if we apply a voltage across the conductor, this cylindrical object here represents a wire or a piece of a wire. If we apply voltage to this wire, then those valence electrons will still move in random directions, but they will have a net displacement. That is, they will drift in a certain direction in addition to their random thermal movement. So here we're going to see that these 2 electrons are moving in arbitrary directions, but on average they're moving to the right. Okay, they're moving wiggly, but they're moving to the right. And now in a real circuit, the electrons, they will not stop here. The electrons will enter this wire here, then they will enter the positive terminal of the battery, and then other electrons will leave the negative terminal of the battery and then enter the wire. And eventually these 2 electrons will make it back to the cylinder. So we have a flow of electrical charges, which is exactly what we call current. So electrical charges that are flowing is what we call current. In the previous slide, those electrical charges were just randomly moving around with no net displacement. That was not current. Current involves the flow of electrical charges. Okay, strictly speaking, electrical current is the rate of flow of charge. It is the amount of charge flowing past a given cross-sectional area in a given amount of time. Okay, here we see a random cross-sectional area, and I got 3 electrons. Those electrons are moving past that cross-sectional area. That gives us current flow. Charges moving past a given cross-sectional area per unit time. Okay, the formula for current is equal to the amount of charge flowing past the cross-sectional area divided by the amount of time that it takes the charges to flow past that cross-sectional area. Okay, the units for current is amps. Okay, so a 1 coulomb per second is an amp. Okay, now if you keep your charge in basic units of coulombs and you keep your time in basic units of seconds, then your current will always come out in basic units of seconds. Okay, what is 1 amp of current? 1 amp of current the current is equal to 1 amp when 1 coulomb of charge flows past a given cross-sectional area in 1 second. Remember, 1 coulomb of charge is equivalent to 6.25 times 10 to the power 18 electrons. So when 6.25 times 10 to the power 8, when 6.25 times 10 to the power 18 electrons flow past a given cross-sectional area in 1 second, that is 1 amp. Now 1 amp is not a trivial amount of current. That is a non-negligible amount. An example, let's say we have 2 coulombs of charge that flows past a given point in a wire every 4 seconds. How much current is flowing through the wire? Okay, remember, current is simply equal to charge divided by time. We are given the amount of charge, 2 coulombs. We're given the amount of time, 4 seconds. Now don't leave your units in coulombs over second. A coulomb divided by a second is an amp. And 2 divided by 4 is 0.5. So the answer is 0.5 amps. So let me erase this. Here's another example. Let's say that we know the current through a certain component in an electrical circuit is 5 amps. How many electrons are flowing through the cross-sectional area of the component in 3 seconds? Now, we always like to use good problem-solving techniques. So first, we got to recognize a relationship between what we are given. Okay, we're given the current, and we are given the amount of time is 3 seconds. So what equation relates current and time? Simply the equation current is equal to charge divided by time. So in this equation here, we need to solve for the amount of charge. And once we find the amount of charge, then we have a conversion factor that relates the amount of electrons to the amount of charge. Now we're going to rewrite this equation as charge is equal to current times time. We simply multiply the left side by time and the right side by time. The amount of current is 5 amps. The amount of time is 3 seconds. Because current basic units are amps and the basic units for time is seconds, then we know the basic units for charge, we're going to end up with the basic units for charge, which is coulombs. So 5 times 3 is 15, and the units are coulombs. Okay, now we got to convert 15 coulombs of charge to electrons. We're going to use our conversion factor and dimensional analysis. So 15 coulombs of charge is equal to 9.38 times 10 to the power 19 electrons. So that's the number of electrons that's going to be flowing through the cross-sectional area every 3 seconds. Very important to realize is that current flows through, not across. I often hear students say, well, so much current flows across this resistor, and I really get offended, and I correct them and remind them that current flows through the resistor, not across the resistor. Current does not flow across a component in normal circumstances. Okay, here we see a piece of a wire, and we're going to see the electrons flowing through the wire, and moving charges mean that we have current. 1 electron went through, then later on 2 went through, Okay, so current flows through, not across. It is incorrect to say current across the resistor is 4 amps. It is incorrect to say the current across the wire is 11 amps. Now, it is correct to say the current through the resistor is 4 amps, and it's also correct to say the current through the wire is 11 amps. Here's the current source symbol. This is basically just an arrow that shows the direction of current flow in a circle. This is an independent DC current source. Okay, what about DC current versus AC current? DC means direct current. That is current that does not change sign or direction over time. That's our focus. So if we look at the current and on the vertical axis versus time on the horizontal axis, we see that the current, in this case, it's a horizontal flat line, which means it's constant. That means that the current never changed directions or signs. Okay, let me show you an example of the current if it changes signs. Okay, it's positive, positive, but it's going negative, going negative, going negative, going negative. Now it's the current went negative. Now that is AC current. Then it went back positive. It changed directions or changed signs. So that is AC current, not the focus of this course. Let me erase let me erase that AC current. This line represents DC current because it never goes negative. The current always flows in the same direction. Now, alternating current or AC current, the focus of AC current analysis changes sign or it changes direction over time. So in this picture here, we plotted current again on the vertical axis and time on the horizontal axis. And we see that the current starts out going positive and it gets more and more positive, but it's still going in the same direction. Let's say it's going to the right. At this instant, it's just more current going to the right. This instant, the current is still positive because it's above zero, positive, but it's a less amount. At this point, we got less current flowing to the right, but it's still positive. But at this instant, the current goes zero, and now the current reverses direction and it starts going to the left. Or we can say that it's negative. At this point, the maximum amount of negative current is flowing. Or I could say that the maximum amount of current is flowing in the left, in the direction going to the left. Then if we get back to this point here, the current goes back positive. This is alternating current. It's alternately changing direction or signs. But that's the focus of AC current analysis. Now let's look at an ideal current source, which have the characteristic that the current remains constant as the voltage across the terminals of the current source varies. So here we have the current on the vertical axis and the voltage or resistance on the horizontal axis. Now notice that regardless of the voltage or resistance, the current has the same value. That is an ideal current source. And we're not going to do much with current sources in this course, but when you get into electronics, then you will be doing a lot more with current sources. Now, a real current source has the characteristic that when the voltage gets too large or resistance gets too large, then the current starts dropping off. Or when the voltage gets too large, the current starts decreasing. Okay, actual DC. Let's look at an actual DC current source. Now, this brings up DC power supplies. They convert the alternating voltage from your wall outlet to a direct voltage or a DC voltage or current that can be varied over a specified range of DC values. Now, power supplies are normally thought of as voltage sources because voltage sources are the most common type of source in the lab. However, current sources are another type of energy source that you will find in some labs. This right here is a picture of a power supply. It can function as a direct current voltage source or a direct current source. So we're at this point in the course, we haven't introduced what voltage is, but here, this is a picture of a real DC current source. So this CC right here, that's kind of hard to see. CC means constant current. This CB right here means constant voltage. So if we're going to use this power supply as a constant current source, we would manipulate these two control knobs right here. In summary, valence electrons are the charge carriers in wires and the simple electrical components of most interest to us. For example, resistors and capacitors and inductors. 1 coulomb of charge is equal to 6.25 times 10 to the power 18 electrons. Electrical current is the amount of charge flowing past a given cross-sectional area in a given amount of time. Current flows through components, not across them. Please don't say that the current across a component is a certain value. Direct current, DC, always flows in the same direction. It does not change signs. Alternating current, AC, alternates between flowing in one direction and the opposite direction. Now, this lecture has been more foundational than actually electrical circuits. In electrical circuits, we spend time trying to find voltage, current, and impedance or resistance. But we have to build our foundation to make our circuit analysis skills better. Thanks for your time. I'm looking forward to seeing you in lecture 3. Have a great day.